Okay, so hi, my name is Alena, and I'll be taking you through question 6 of Spring 25 midterm. So this question is all about the EU CPA game in lecture, or in this question, it's called EU CMA, and it's a simplified version of it that determines whether a cryptographic scheme is secure or not. In this game, you'll be the adversary and you'll be playing against some challenger. And how the game goes is that you first send the challenger a message, and then the challenger will give back the valid MAC of that message. And then you will need to output some M prime that is not the original M, as well as a tag prime, and you win if this tag prime is a valid MAC for the new message that you just sent with non-negligible probability. If you win and you are able to find this new message and tag combination, then we say that the scheme is insecure. But if you're not able to find this new message as well as a valid tag for that new message, then we say the scheme is secure. So this question will take us through various schemes, and we have to either say that the scheme is secure, or we have to find a counterexample of what we would send to prove that it's insecure. Okay, cool. So for this first part, the scheme is basically the MAC is going to use CBC encryption given some key, and it's going to encrypt the hash of the message and finally give back the IV as well as the ciphertext. Okay, cool. And now we need to find some new message and then give back new IV and a new ciphertext that's valid for that new message. And I think this question is very intimidating at first, so I'll try to break the problem down further before diving into it. I think the first step for this question is remembering what CBC encryption is, right? So CBC mode is when we have the ith ciphertext is going to equal the encryption of the previous block of ciphertext XORed with the current block of the message, where the first block or the 0th block of ciphertext is going to be the IV. However, in this question, we're only going to work with one block, I guess you could say. So here, the original tag, which equals IV, and the original ciphertext is just going to be IV, and then the encryption of that IV XORed with the message that we sent them originally. Okay, and then I think something else that is really important that you have a good understanding of is the properties of XOR, because the solution to this question is basically going to come down to how well we can manipulate XORs to manipulate the ciphertext into what we want given the new message. So some XOR properties that will be important for this question is, first of all, if you XOR something with itself, that's going to equal 0. And then if you XOR something with 0, you'll just get the original thing back. So if you XOR something with the same thing twice, then you'll just get the original thing back as well. Okay, so now let's dive a little bit into the problem slowly. So Yeah, so this was our original tag, with this being C. And what we need to find is a new tag, which is a new IV, as well as a new ciphertext, where we can expand this ciphertext out using the definition of CBC encryption. So it's going to be the encryption of whatever we choose our new IV to be, XORed with our new message, whatever we choose that to be. Okay, and the hard part about this question is the fact that we don't have the key, right? So it's very hard to choose something and then encrypt it. What would be a lot easier is to be able to manipulate this whole term into something we already have using this XOR that is already encrypted, if that makes sense. So what terms do we have? We need this to be in terms of the original IV, our new message, the original message, or the original ciphertext. These are kind of the things that are readily available to us. And this ciphertext is kind of going to be our key here, because as we've seen, this was already encrypted. So this kind of solves our problem of not being able to just encrypt anything. So that will be that. I think that is a good baseline for our solution. So now my line of reasoning is, what if we can define some IV prime such that this C prime, so this is C prime, so C prime equals the encryption of this new IV XORed with H of M prime equals our original ciphertext. Okay, so, and this equals the encryption of the old IV XORed with the, let me move this a little bit, old message. If we can get these to equal together, then our final solution can just be whatever this IV prime equals, comma, the original ciphertext. And from here, this is kind of just like algebra, as you can think of it. We eliminate our problem of encrypting because both sides have been encrypted, and we just have to manipulate whatever's inside the encryption. Okay, so we want to isolate IV, so we can just do IV HM prime, and then we want to get rid of the HM prime on both sides. Or on the left side. And we get that our original IV, or sorry, our new IV will be the original IV XORed with the hash of the original message XORed with our new message. And this is what goes in here. So, and you can always plug the original IV back in and see if it all works out. But yeah, basically now we found a new M prime, and given that we okay, so this scheme is insecure. Our query message can be anything, the original M can be anything, and our M prime can be anything. And we have proved that this is insecure because whatever M prime is, we can simply return back this IV XORed with HM XORed with HM prime, comma, the original ciphertext, and this will be valid for any M prime and any M. Okay, that is one of the harder parts of this question, so yeah, might take some staring at, but we'll move on to the next question. Okay, so this scheme is pretty similar to the last scheme, except we're using CTR encryption instead of CBC. So we can go through a similar thought process. Oh, there's not a lot of room here, but we can just go at the top. Yeah, so CTR, and first we'll go through what CTR is. CTR is for the ith cipher block. We're going to encrypt our IV, and then CTR is the one that has a counter, so we add IV to whatever ith block we're on, and then we XOR this with the ith block of our message. But again, we are only dealing with one block, so all in all, our ciphertext will be the encryption of our IV XORed with H of the original message, the hash of the original message. And this means our original tag is going to be the IV, and then, yeah, as we just put above, XORed with H of M. And we want our new tag to be something like a new IV, and then the encryption of this new IV XORed with the hash of our new message. And following a similar thought process as the last part, this encryption is what's going to give us problems. And specifically, if we just choose any old IV, this is going to make things really hard for us because we can't just encrypt any old IV. And so this hints at us that maybe since our original ciphertext already has this encryption of the original IV, we can use the original ciphertext to our advantage, maybe XOR it with some terms in order to mold this tag into what we want. So what this means is that our new tag will actually be holding the original, IV constant, and then our tag actually becomes encrypting the original IV XORed with the hash of our new message. Okay, and now all we need to do is to somehow get rid of this encryption term using our terms like the IV ciphertext message or our new message by using like XORing. And so notice that what we kind of want to do is cancel out, okay, so our original ciphertext is this term. But we kind of want to cancel out, but we actually want this to be H of M prime. So what we can do is we can XOR with another H of M to cancel that one out, and then XOR it with H of M prime to get that in. So what this means is that now this is kind of a valid tag. We said that this scheme is insecure in our counter example. It doesn't matter what the old message is, and it doesn't matter what our new message is. All we know is that we just have to return the original IV as well as the ciphertext XORed with the old, the hash of the old message to like cancel it out, and then the XOR of the new message to kind of have that appear into our answer. And this will be valid for any h. This will be a valid tag for any h prime. Okay. So for the next couple parts, we're going to be now doing signature schemes, but the game remains pretty similar. So for this question, in order to sign a message with secret key SK, we'll use this scheme, M to the D mod N, where D is our secret key. So for this for this scheme, the key idea here is to realize that S and M are proportional in terms of their exponents. And what I mean by this is that we can easily manipulate exponents using some, like, the property that like xa to the b equals xab, and then it doesn't really matter in this scheme like what the a and b kind of like multiply to. So one example of this is, let's say we have m prime be m squared, then our signature just becomes m2 to the d mod n, which is m2d to the mod n, and this actually just equals s squared. And so this is actually valid. So we actually can answer the question with this solution, where a query message can be anything. And then if our solution method is m squared, then our signature will be s squared. However, you could have just raised m to like any power, and as long as you raise the signature to the same power, then it would have been a valid solution, valid counterexample to the scheme. Okay, so on to the last part. We'll have the signature of m is the hash of the original message plus x times m mod p. I think actually this p should be p minus 1. Yeah, this should be p minus 1. And where x is our secret key. And the key idea for this this question is that once you write out the equation for assigning the message, you realize that we know s, we know m, as well as the hash of m, and so we can actually solve for the secret key, and then just sign. Now that we have the secret key, we can literally sign any message, and it will be valid. So if we solve this, we get that x equals s minus the hash of m times the inverse of m. And then, yeah, now that we have x, we can sign any message. So if we have the message m prime, then our s prime is just going to be signing using x and m prime, just doing some algebra and plugging it in. We get that our final signature is going to be the hash of m prime, and then plugging in the x that we derived, and then we still have to multiply by this m prime, p minus 1. Okay, cool. And this is, literally our answer. So our final answer is that this is insecure because given any message, and we don't care what m prime is either, because as we said, now that we have the secret key, we can literally sign anything, or we'll know the signature for anything, and then we can put in our answer. Okay, so that's all the parts for this question. Hopefully that helped a bit.